So we've seen so far that the absolute value of the difference of two real numbers defines a specific case of what in the more general case we call a metric, a way of measuring the distance between any 2 points of a set. As long as my distance notion, my distance function, satisfies the 4 properties of non-negativity, non-degeneracy, symmetry, and the triangle inequality, that function is going to define for me a way to measure distances, a metric. So in this video, we want to look at some more examples of metrics besides the one that we're already familiar with, by looking at some examples of metrics not on the real numbers, but on n-dimensional Euclidean space. We'll look at a couple of examples there. As well as, and this is the one that's going to be most interesting for us for the rest of our semester, examples of metrics that we can set down on functions that will allow us to measure how close or how far apart are two functions of a real variable. And that is going to be the key notion that we're going to need in order to talk about how to approximate functions. We have to be able to tell how close we got in order to approximate a function arbitrarily closely. So let's look at those examples together and sort of set the table for what we're going to hang on to when we go to approximate functions later on. So metrics are going to let us measure the closeness of things, closeness of elements of a set. And ultimately, those things are going to also include functions. And so this is going to be our first taste of what that ultimately looks like. The one metric that we've had experience with so far, right, is the metric defined by the absolute value of the difference between two real numbers. This we might think of as just being the same thing as measuring a distance along the real number line, right? In the ordinary Euclidean sense of the word distance, right? High school geometry style distance on the real number line. And so you might ask, well, if we take that up one notch and think about distances on, let's say, the xy plane, right, or in three-dimensional space, does the ordinary Euclidean distance still define for us a metric on those spaces? And the answer is yes. Right? If I just take the ordinary distance formula in n-dimensional Euclidean space, I take the difference of the first coordinates of my 2 points and I subtract it and I square them, and then I add that to the square of the difference between the second coordinates, add that to the square of the difference between the third coordinates, and so on, and then take the square root of that whole thing, then I'm going to get a Euclidean distance measurement that actually does satisfy the tenets of being a distance function, a metric. So that's nothing too fancy, right? The only thing that I'm going to add to that is that we're going to call that metric d sub 2. And we'll see why we call it d sub 2 in a minute. But this is the ordinary Euclidean metric. It just measures the regular distance along a Euclidean straight line between 2 points in the xy plane, or in any n-dimensional Euclidean space, really. So why d sub 2? What is that 2 actually doing? Where is it coming from? Well, that 2 is coming from the exponents that I chose to put on the differences here between my coordinates, and also the index of the radical that I placed out in front. This is square root, so it's a radical with an index of 2. Well, what if we picked a different index on that radical? Instead of picking an index of 2, what if we picked, I don't know, an index that we call p? If I do that, then I get a notion that is called the p metric distance. So I do have to tweak one little thing in this formula that I just wrote. We're taking the pth power of the distance between the first coordinates and the second coordinates and so on, adding them together, taking the pth root at the end of the day. Well, I can't actually do that unless I know that my quantity underneath the radical is non-negative. And so where we see all the parentheses in here, what we really want are absolute values. So what's going to happen if I tweak that value of p? How is it measuring distance differently than the standard Euclidean metric? Well, let's pick a couple of points where maybe the distance is, let's say it's a Euclidean distance of around 4. So I'll try and get it to be as close to 4 as I can right here. Well, what happens if I crank that value of p up to, I don't know, 3? It looks like the 3 distance will be less than the Euclidean distance was, about 3.68. If I crank it up to, I don't know, 10 or something, we get a smaller distance yet. So it's just giving me a different way of measuring the distance between these 2 points. When p is equal to 2, we get the Euclidean distance. If I dial the p all the way down to 1, I get a new distance that, take a look at what it's actually doing. It's actually measuring the difference in the x coordinates and the difference in the y coordinates, and it's just adding the two of those things together. So this one distance is sometimes called the taxicab metric. in other words, if these 2 points are separated by, let's say, 4 units of horizontal distance and 3 units of vertical distance, it's like I'm in a taxi cab and I need to get 4 blocks to my east and I need to get 3 blocks to my north. Well, no matter which direction the taxi cab takes, its total distance that it's going to drive, if it can only move east and north, is it's going to have to drive 4 blocks to the east, it's going to have to drive 3 blocks to the north, and so it's going to drive a total of 7 blocks. So this d sub 1 metric measures in kind of an interesting way that we can also depict geometrically. So the 1 metric, the taxicab metric, measures distance like this. It gets the distance between these 2 points to be 7. The Euclidean metric gets the distance between those same 2 points, this is as the crow flies, to be equal to about 5. But then different values of p are going to give me different values for this metric. And so these are a couple of different ways of measuring distances between points in the xy plane using these p metrics. Okay, but now when things get really interesting is if we want to try and measure the distance between functions. And there are probably, an entire semester's worth of different answers to the question, how should we measure the distance between 2 functions? And so we're just going to look at a couple. And the first one that I want to look at is a way of measuring the distance between 2 functions that takes all of the values of both functions into account. Because that's one of the issues with functions, is that generally they have infinitely many different inputs to worry about and infinitely many different outputs from those inputs. And so what we might want to do is take some sort of an operation that considers the functions in their entirety. One way of doing that might be to look at the area in between those 2 curves. And if I want to know something about the area in between those 2 graphs...
Yeah, now that's what I'm talking about.
Go away. This isn't calculus class. So if I want to know something about the area in between 2 graphs, I probably want, yes, an integral. So if I take the integral of the difference of f and g, that's not quite going to get me exactly what I want. It's not going to give me a metric necessarily, because I don't know for sure that this integral is going to be non-negative. So in order to make this integral non-negative, what I want to do is slap some absolute values around the difference of f with g. And in doing so, I get something called the 1 metric. So this measures literally the absolute area in between the graphs of my 2 functions. And we can check that that actually defines, there's some fussy details that we're going to elide this semester, but that defines for us, in a way, a metric on the space of functions. But of course, it's not the only way for us to measure metric distance between 2 functions, because we might also consider this exponent, this hidden exponent on top of my absolute value of the difference of f with g, and tweak that exponent around. If I put a p exponent on top of that, and I put a pth root on the outside, then what I get are a family of metrics on functions that are called the Lebesgue metrics, the pth Lebesgue distance, if you like. So here I have 2 functions f and g over here, they're graphs, and I've shaded a function which is the absolute value, the pth power of the absolute value of the difference of these 2 functions. And so when p is equal to 1, we get the d1 distance. The actual absolute area between these 2 graphs was about 2.22. But if I tweak the value of p, if I increase it from 1 to 2, I get a different way of measuring this distance. If I increase p still further, I'm going to get different ways. Here's the 5 metric, the 5 distance between these 2 functions is about 1.21. And so different p's are going to give me different values. Notice I'm taking the pth power, but then I'm also taking the pth root of that area. And so as this area is getting bigger, I'm taking successively larger roots of it, which is why my numbers, my pth metrics, are not getting too out of control. But you'll notice something interesting is happening as I'm raising the value of p. It seems like most of the area that we're getting is sort of concentrating around the middle of this graph. In fact, it's concentrating around the place where the graphs are the furthest apart. And as I'm jacking up that value of p, the largest value of this pth power of the differences is sort of blowing up to infinity and concentrating itself around that place where my 2 functions are the furthest apart from one another. And so as it happens, if I keep increasing that value of p, in the limit as p tends to infinity, what it ends up measuring is it ends up measuring exactly the largest difference in absolute value between the values of my 2 functions on the interval that is their common domain of definition. And that metric we call the infinity metric, or sometimes we call it the uniform metric. It's defined as the supremum, because we don't necessarily know that there'll be a maximum. It really depends on the properties of the domain. So supremum is a safe way to do it, keeping in mind that the supremum could be infinite if my domain is unbounded or if I have other untoward behavior happening. But it's the supremum of the absolute value of the difference between my two functions. So it's, in a way, it's the length of the largest vertical line segment that I can draw in between the graphs of my two functions on their common domain of definition. So we had a bunch of these integral Lebesgue metrics, and then as it turns out, which we won't prove, but you are certainly welcome to look up a proof of this, that as p tends to infinity, the values of these Lebesgue metrics are going to approach this infinity metric, this uniform metric, which is the largest vertical distance between my two graphs that I can find at any point. So this is sort of a catalog of a variety of different metrics that are going to potentially be of interest to us, and especially the metrics on functions that we're going to start to try and use in the next couple of videos to discover some new properties of continuous functions, and particularly of sequences of functions, that can help us to begin our journey toward the process of how to approximate one function by other functions arbitrarily closely.